But she does it so often, I'm not scared. So last year in pre-calculus, we talked about continuous functions, and we said, I think it's a great definition that these authors use in both the pre-calculus and the calculus book, is that a continuous function can be sketched in one continuous motion without lifting the pencil. Right? And if you remember in pre-calculus, I gave you that extra coming out of the continuous function. When you look at every part of it with the pencil. If a function is not continuous, we say that it's discontinuous at that point, or it has a point of discontinuity. And kind of the weird part that we're going to go into today, and I don't know how much you need to dwell on this, but we could say that a function is discontinuous at a point that's not even in the domain. Sometimes we just enable it's continuous over its entire domain. So you can kind of argue about whether a function is continuous or not continuous, whether or not you want to consider points not in the domain. So just kind of keep that in mind as we go through some of this. We'll look at some points later. But just know that you could say, like for me, I'm going to see an example right now. If I said y equals the square root of x, for me, I like to say I think that's a continuous function. Because if I graphed y equals square root of x, it starts at 0 and it goes up like this, and I can graph that without ever lifting my pencil. But technically, if I said, give me a point where it's not continuous, I could say it's not continuous at -1, because there's not a value at -1. But you could also say it's continuous over its entire domain. So I feel like sometimes math people like to figure out ways that they can argue about stuff. And this is one of the things that you can do. I got an argument this summer about whether it's a function if it's not in the domain, and really the result was it depends on how you interpret it. And so just know that that's kind of out there, and it does seem kind of like conflicting ways of thinking about it, but both are correct. Okay. What you need to know are the different types of discontinuities, and we took long notes in pre-calculus today. I'm giving them the notes over types of discontinuities. So I'm just going to review them with you. A removable discontinuity is like a hole in the graph. A real nice definition is a removable discontinuity could be filled in with one point. So a nice example of that would be like if you could put your pencil on the one place where it's not continuous and fill it in, it becomes a removable discontinuity. And I always want to put an E in removable, but I don't think there's those two. Or maybe there is. I called it on the day. I like alternate my colors because I don't really things wrong. A jump discontinuity is exactly what it sounds like. It's a jump in the graph, or we can say a gap in the graph. We've seen a lot of those with our piecewise functions where a limit doesn't exist. So like a nice example of that would be like a step function. That's a jump discontinuity. Here it seems not like actually. I'm just not going to put that. Right? Like it jumps. You can't just fill it in with one dot because there's a jump, a gap. An infinite discontinuity is a vertical asymptote. Right? You definitely have to pick your pencil up when there's an asymptote to graph on either side of it. What was this example? Did we talk about oscillating discontinuity last year? When we talked about the calculus, so, like, this is an example of an oscillating discontinuity. It's one of those weird functions that we looked at last week. Oh, well, we're on that worksheet. Remember, like, it went up and down over the a limit. And so oscillating means like it kind of like goes up and down, but it's still approaching that value. And so the one on our homework the other day, like as it went to infinity, like it went like this. With that, and Tyler, I think you said you thought it was 0, and we said it was 0, even though it kind of went around. That graph, in your book. This. We talk about it, and then later on in the year, someone always says, I really want to see some of the boxes. This example of this is y equals sine of 1 over x. So at 0, it has an oscillating discontinuity. Because you can't plug 0 in there, but it is approaching 0. Just kind of beautiful. All three of these are not removable. So really, it's important to know the difference between removable and non-removable. So this would be non-removable. Oh look, it's only there all here. I struggled drawing my destiny. Can you see those circles, those open circles on yours? So like this one is continuous. Fill in, but it's hard to see on these. But both of these, what's the difference between B and C? Oh, I know. Okay, so B, there's an open circle right there. So if you can't see that on yours, this would be removable. C is also removable, but the difference is it has that little dot up there, which means this would be a piecewise function. Because it would say at 0 you get 2, but then it would have the function for everywhere else but 0. This is also removable. And then the rest of these, I could have stayed fine there and drawn all those out. We have our jump, our infinite, oscillate. And I just copied those right there. So let's have this on your homework. It says, find and identify the points of discontinuity of y equals 3 over x minus 1 squared. Point of discontinuity we're talking about in the domain. We're talking about what x can't be. And so if they're talking about points of discontinuity, they're kind of talking about what's not in the domain. So looking at this problem, what do you know you could never plug in for this? 1, because 1 minus 1 would give you 0 on the bottom. So points of discontinuity, x equals 1. What does it say to identify what kind it is? I think on your homework it says, what kind of discontinuity is that? So the question is, could you identify this without graphing it? Looking at this equation, do you know if it's removable? Is it a jump? Is it an infinite? Is it oscillate? Because there's a vertical asymptote there. And you could look at your calculators to help you today. But yes, we could say this was an infinite discontinuity. I'm not sure how it's labeled on your homework, but sometimes instead of asking you to find the point of discontinuity, they tell you to say where it is continuous. And so that's like writing out the domain of that. So I'm just going to do that even though the math here. If I wrote where it is continuous, it would be continuous everywhere but 1. Remember how to write that? Like if you're using interval notation, how you could write out everything except for skipping over 1. Not including 1, right? And then we skip over 1. So just be aware in the homework, if it asks you to give the interval where it is continuous, you still think about where it's not continuous, and then you write it as an interval. Function is continuous on an interval if and only if it's continuous at every point of the interval. A continuous function is one that's continuous at every point of its domain. Continuous function need not be continuous on every interval. This is what I was talking about, how this whole so is the function y equals 1 over x a continuous function? And this is where I find it conflicting information, because we could say, what is the domain of this function? What would you say is the domain of that, you know? What can't x be? 0. So the domain would be everything but 0. So its domain would be negative infinity to 0, 0 to infinity. So I could say a continuous function is a function that's continuous at every point of its domain. I could say, is this a continuous function? Yes. Continuous over its domain. Because it is continuous everywhere between negative infinity to 0 and 0 to infinity. But you could also say that, is this a continuous function? No, it is not continuous at x equals 0. And again, I understand that's conflicting information, and I don't try to give you that to confuse you, but I just want you to be aware that depending on how you say it, you could say it's continuous over its domain, or you could say it's not continuous at x equals 0, or x equals 0. So again, just kind of be cautious. I feel like you can't just say yes or no, right? Like you have to explain why you're saying yes or no, and as long as you explain correctly, both of them. I don't know why if you want me to address this, you know this, right? Well, on the homework, I don't think you do that, but okay. Graph and find any points of discontinuity, label as removable or non-removable. So, piecewise functions, you should be able to figure out pretty quickly where the points of discontinuity are, and you might not even need to graph it. We'll graph this first one. But here's what I want you to think about. 3 minus x. That's a linear function. Yes? A linear function is continuous. X over 2 plus 1. Linear function. Linear function continuous. So where's the only point that you should be worried about if it's continuous or not? Where it meets up. So we could graph this to see if it meets up. But do you have a better, more efficient way that we can see if it meets up without having to graph it? I'm going to draw that one in there to help me, right? You don't have to do it, but it helps me quickly. So when x is less than 2, 3 minus x, you can just make an xy chart. I hope that you feel pretty good with slope-intercept form, that you could go up here to 3. It has a slope of negative 1. You go down 1, over 1, down 1, over 1. Now look at this. On the other side, I can plug 2 in there to start, because I'm starting at 2. 2 over 2 is 1 plus 1. And at 2, I'm starting at 1. Then I would go up 1 over 2, up 1 over 2. Is that right? No. shouldn't this be... Why is my graph not? But if I plug 2 in there, don't I get... Oh, I get 2, not 1. I said 1 plus 1 was 1. I get up here. See, at least I checked my work, because I knew I was wrong. In my head, instead of starting over here at the y-intercept of 1, which you totally could do, you say up 1 over 2 and make your mark there. I was trying to just plug 2 in there, but I said 1 plus 1 was 1. Is that a continuous function? What kind of possibility? You just have to say removable or not removable. Not removable is that it's anything but just the one to one. Not continuous at x equals 2. And it is not removable because they didn't meet up together. If they both met up right there at 1, and it was just 1 over 2, but you don't have to graph to see if these meet up, because you could have just plugged 2 in for both of these, right? If I plug 2 in here, 3 minus 2 is 1. If I plug 2 in here, 1 plus 1 is 2. And since 1 does not equal 2, I knew that they didn't match up, that it was a gap in the graph. Even if they did meet up, could this have been a continuous function? Because neither one of those are included, right? So there's going to be an open circle even if they met up. So that's another difference. And as we go forward, we're going to talk more about dealing with piecewise functions without always having to graph it. This is a problem in the book, and sometimes people just get confused by the example or the directions. Once we do it, you'll understand what it's asking. It says, give a formula for the extended function that is continuous at the indicated point. So the issue is, if I plug -3 in here right now, I get an undefined function. But just like with limits, we don't just say it doesn't exist. If that happens, we try to do some algebra. So when it says find the extended function, it means try to simplify it so that you could plug that number in there. All right. So this means like factor slash simplify. So I could factor this into x minus 3, x plus 3. And then I can cancel that out. So the extended function would be f of x equals x minus 3. In your homework, they're going to talk about like making some piecewise functions to make things defined, and we'll kind of see how you do on those. I'm going to let you look at those before I just do one for you. But thinking about writing your own piecewise functions to make something that's not continuous, kind of an interesting idea. There's some of the textbook I used to assign, so we'll see how we do on those. All right, we got our first theorem of the year. Intermediate value theorem, IVT, it's okay to abbreviate it. It's not one that's used very often, but sometimes on the AP exam, on the written part, you can use some theorems to help you short what you have to say. So it says a function that is continuous on a closed interval from a to b takes on every value between a and b. Sorry, f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c in the interval a to b. Got it? Here's the thing. When we talk about continuous functions, we're talking about x values. So when we say that a function is continuous, these are the x values. And what the intermediate value theorem says, that if it's continuous on the x-axis from A to B, then the y-axis points that coordinate to that, it's also continuous. So it's saying, so you have this point A here, and up here you get the y value, which is f of A. Then you have your B. So up here we can say that f of B would be the y value. So the intermediate value theorem says if all these x values are used from A to B, then all these y values also have to be used from A to B. And so that's what that whole C is. If you pick some random value in between A and B, they call it C, there has to be a coordinating y value. And we'll look at a question like that tomorrow, but we use this theorem without ever thinking about it. If you have a graph, and you know, trying to think something here. If you know that at f of 2, it's 7, and at f of 5, it's negative 3, can we say we know it crossed the x-axis somewhere between 2 and 5? Because if it went from 7 to negative 3, we know somewhere it was 0. And so, if we know this is continuous, we can say, so like, if, f and if, f of x is continuous, we can say we know there's a 0 between 2 and 5 without ever looking at a graph, without ever knowing an equation. And so sometimes it's like, yeah, that makes sense. If all the x's are used, all the y's are used, how would that come up in a problem? That's how that could come up. That I could say, well, I know if it's continuous from 2 to 5, then it's continuous from here and it crossed the x-axis. And so we're going to start tomorrow. We'll buy the intermediate values. And then the last thing I want to say is, why are we talking about continuity in the midst of all these limits? Is we want to think about how we could define a continuous function using limits. So it's a very nice definition to say a continuous function, you never have to repeat one. But mathematically, we can define continuity using limits. So how do we define if a limit exists? What was that definition? I don't know if a limit exists as if we're just So we can talk about a function is continuous at a point C, starting the same way. We can say if the limit as x approaches C from the left equals the limit as x approaches C to the right, in this case, what I have shown right now, the limit as x approaching C from the left equals the limit as x approaches C from the right. But is this a continuous function? What else would I have to say in order for this to be a continuous function? This has to equal, right? This would have to be filled in, which means at C, we better get the same thing that our limits equal, right? And so we can say like, so to be continuous, we have to add this extra part. The limits for the left and the right have to equal each other, but it also has to equal what happens when you plug C in. Because if not, it might have a limit, but it might not be continuous. And we're going to get to a point of talking about proving that something's continuous. And just this one sentence right here, if you can say that, then you can prove it. So your homework is on the computer. If you would rather me print out a copy for you, or paper homework, I don't have to do that. Just let me know and I can put those out. But if you have time, or if you have access to home, I really hope that you can do it on my You might not like something you're right or wrong, so I hope that it helps you. Thank you. Alright, but if you want a paper copy, just let me know. Or my free copy at 10.